Okay, thank you everybody for joining for this tutorial. Together with Abdul Vassey, Suparna Chatterjee, we're going to present a tutorial on deep learning and specifically looking into the aspects of systems and responsibility. So our goal is to truly bring up the major opportunities that exist in the field, but at the same time highlight specific problems, both from a systems perspective, design, implementation, scalability, and from an ethics perspective. Okay. And then with all of that, we hope to also highlight several opportunities that exist for data management in particular, but in general for computer science, to utilize and extend and improve deep learning technology. And in addition, in the end, we're going to present our view for what we call a new kind of AI, which is actually both new and old, where we think some of these problems, some of the systems and responsibility problems can be treated a little bit better. Okay, so with that, let's start with a quick introduction. So first of all, when we generally refer to AI, the idea is that we start with with data and we end up with predictions. Okay, and in principle, for the context of this presentation, when we refer to AI, we really mean machine learning, and specifically, we're going to be looking into deep learning techniques. Now, technology like that is being utilized these days broadly and increasingly in different areas of our lives. In society and in sciences. And so these are some of the examples that you probably all of you are aware, such as Google or Facebook or other internet-based services utilizing AI technology to create to create their services. Okay, so for example, advertisements is a big user of AI technology. But even other aspects where it might not be obvious to everyone, such as Uber using AI to decide what should be the price for the next ride. So this is something completely dynamic that takes into account the different context, the different user, and so on and so forth at the right time. And even other aspects that traditionally happened with more traditional analytical tools, such as placing products in shelves in grocery stores or in other big stores. And of course, several fintech applications are also extremely interesting. In general, what we're doing with learning technology is that we learn from the data as opposed to manually modeling the world. Okay, and really, when you think about extremely complex problems where the challenges are so big, this is where the potential is. And so, for example, when we have problems where humans, potentially they could have created a manual, mathematical model, but maybe it's extremely hard to do, and so it's more likely to fail in creating that mathematical model. Or for most humans, it would take a ton of time, and so we cannot afford having absolute experts at a time creating models for every particular problem. And so instead, we could have a more automated approach relying on learning techniques. And here's some examples that are more kind of down-to-earth examples to understand. So if we look at just sheer numbers of how many, for example, medical errors are happening every year, and these are human errors, and unavoidable for many different reasons, no matter how much structure we put around the whole process, or how many car accidents that are due to human error. So if it was possible, even for some percentage of those errors to eliminate them, then we would really save human lives. And so this is where the excitement, the true excitement for this technology lies from our perspective. The ability to minimize human error as much as possible in cases where it is extremely critical. and the side effects are they're really affecting human life. Of course, this whole discussion depends on the context and what is really the probability of error. So, for example, when we're discussing about medical errors, it is really different if the discussion is about a state-of-the-art top doctor in a state-of-the-art hospital versus kind of a mediocre doctor in some remote place of the world. And so the opportunity to improve human life is different depending on the context, but still the need is very real. So so it's not as simple as saying that, oh, I would have an expert doctor, because not everybody has access to these expert doctors. Okay, so with that, that is the goal of all of science and technology. And so one thing that we would like to highlight is that, and even though we don't want to go into these details in this tutorial, is that really when we discuss machine learning and AI technology, it's not really the models, it's not really one aspect of the problem, but so many different technologies have to come together to make it possible. Okay. And in fact, just to throw some philosophy here, this has been a goal of of all of humanity for thousands of years. And so even if you go back to ancient Greece, you'll find texts where people have been dreaming about ways to improve human life through automation. Okay, so there were even texts where the notion of a robot that serves human beings actually manifestates in those texts. Okay. So with that, what we're going to do in this tutorial, we're going to discuss the opportunities, we're going to discuss systems and responsibility problems, and in the end, discuss a new kind of AI. And again, focusing on deep learning. The tutorial will have 3 parts. The first part will be presented by Vasey, and it will give the systems perspective on deep learning, highlighting specific systems techniques that we can utilize and also open problems. Then we're going to go to the second part where Subarna is going to present several different aspects that have to do with responsibility and bias. And then for the last part, I am going to take over again and present this new AI method that we call machine knowing, and can help with some of those issues. The tutorial itself is designed in a way that for the most part, it is accessible to everybody with some basic data management and data systems knowledge, and it doesn't require any specific AI or deep learning expertise. We're gonna provide enough background for people to be able to follow. And there's also, for those of you that are interested in going into this material in more detail, there's also a website along with a paper that we're going to highlight, and you can find more information in there. Okay, so with that, we are going to move now on with the first part of the tutorial.
In the first part of the tutorial, we're going to look at research that develops techniques to trade off between various metrics, such as accuracy, training time, and memory usage during deep learning training and deployment. Before we do that, however, let's have a refresher on the fundamentals of deep learning. And specifically, we're going to take a systems angle to understand deep learning training and deployment. The central question in machine learning is to map the relationship between one set of objects belonging to the input space to another set of objects belonging to the output space. In computer vision, this relationship is learned between images and their labels, whereas in machine translation, for instance, this relationship is learned between words in 2 different languages. In supervised learning, this relationship is learned from a training data set, which consists of members of both the input domain and the output domain. So in this particular example, we have images as well as their labels. When we're applying deep learning in a supervised fashion, the mapping takes the form of a deep neural network, and the network is trained on the training data set. A neural network takes a data item as an input and produces a probability distribution over the labels. A network may consist of several layers, and every layer has several neurons. Every neuron takes input from every other neuron from the previous layer and produces or contributes one output that goes on to the next layer. Within a neuron, there is a weight associated with every input. The neuron applies the set of weights to the inputs, aggregates the results, and passes the aggregated value through a nonlinear transformation to produce an output. So we can think of a neural network as a bunch of weights, and the training process of a neural network amounts to setting the weights in such a way that the mapping between the input data items and their labels is correctly learned. The training process proceeds in many different steps. The first step is to initialize all the weights in the neural network using small random numbers. Once that's happened, then a forward pass is performed on the network to produce an output. The next step is to quantify how close the output is to the actual label using a loss function. And then we compute the gradient of the loss. Mathematically, this gradient represents the direction in which the loss would increase the fastest. Since we are interested in decreasing the loss, that is, we want the network to closely match the actual labels. What we do is we move in the opposite direction of the gradient. And we adjust all the weights slightly in that opposite direction, and this happens during the backward pass. Here, eta is a hyperparameter, which we call the learning rate, that sort of controls for how eagerly we're going to make these updates during the backward pass. Of course, the training process does not happen for a single data item, but happens for all data items in the training set. And this happens over many different iterations. This process is called gradient descent, that is removing in the opposite direction of the gradient. Over multiple rounds of training, the loss overall gets minimized. And we can stop the training based on a few different criteria. We can stop once the training budget has been exhausted, or once we've met a certain loss criteria. This parameter in terms of when to stop training is controlled by the designer of the deep learning pipeline. And if for some reason the loss does not decrease as expected, there are several ways to debug this process by either using random restarts or properly adjusting the learning rate using some learning rate schedule or some schedule for how the learning rate can be adjusted with the training process. Once a neural network has been trained, performing inference only requires a forward pass on the neural network parameters. In modern deep learning pipelines, because of increasing complexity, we can also use ensembles of neural networks where multiple networks are trained to perform the same task, and the output of the networks is then aggregated to produce the final output. When we look at a neural network from a computational perspective, they consist of several matrix multiplication operations for all of the different layers in the neural network, and these ultimately map to multiply and accumulate operations, and these operations lend themselves quite well to modern GPUs with massive amount of data parallelism. When we look at a neural network from a data movement perspective, on the other hand, what we observe is that the forward pass produces intermediate results for every layer. These intermediate results are stored in the GPU memory as they are required during the backward pass. So they're stored and then reused during the backward pass. The memory footprint of the neural network comes from the training data, the network weights, and the intermediate results. During training, the majority of the footprint comes from the intermediate results because they're produced for every single layer in the network. During inference, because there is no backward pass, so these intermediate results do not need to be stored, and therefore the memory footprint consists of only training data and network weights, and is significantly less than that of the training process. We talked about training and deployment of deep neural networks because that is something we're going to focus on for the rest of this section of the tutorial. But these processes of training and deploying neural networks reside within a complex deep learning pipeline that originates from data collection and goes all the way to model deployment as well as design. When we are examining a neural network, we care about its quality, that is the accuracy of the network, as well as the resources required to train it. And these resources manifest themselves in terms of time and memory usage. Existing research to improve deep learning pipelines often trade off between these metrics. First of all, let us look at some research directions that trade off accuracy for some improvement in time and memory usage. Compression is one general approach to achieve this trade-off. In compression, various data items in the neural network training and deployment phase, which include training data, network weights, or intermediate results, are compressed. There are various ways to achieve this compression. One compression technique applied in deep learning pipelines is that of quantization. That is to reduce the precision of weights and intermediate results, making the network faster to train and less expensive in terms of memory usage and storage. Quantization can happen in a variety of different ways. First, there is research proposal to reduce the precision of numbers within the network from their 32 or 64 bits representation to k bits. This makes it both easy to operate on as well as more efficient to store these intermediate results as well as network weights. K can be anywhere from half of the precision of the original number down to 1. In addition to reducing the precision of the numbers, there is also work on converting floating point numbers into integers that are easier to operate on compared to the original floating point numbers. Finally, research from the machine learning and systems community also proposed using hardware knowledge to inform how and what to quantize. Pruning is another way to achieve compression. The general strategy is to remove weights that are less useful, and there are various methods designed to achieve this. Magnitude-based pruning is one of these techniques where weights that have the smallest magnitude, which in this case are highlighted in red, are pruned, and this process can be done after training and is completely independent of the training data set. So it's pretty easy to employ, as we only need to consider the values of the individual weights. Another way to prune that is more effective but requires access to the training data set is to first measure how parameters affect the training loss and then prune the ones that have the least effect. As I said earlier, this produces better result than magnitude-based pruning, but requires access to either a training data set or some validation set. Finally, there are approaches that take into account hardware properties to decide how and what to prune in a neural network. Distillation is another technique to achieve compression. The high-level idea is to train a smaller model to mimic a larger model. The larger model is called the teacher model, and the smaller model is called the student model. Distillation proceeds as follows. Training data is passed through both the teacher and the student network, producing an output for each of the networks. We quantify both the empirical loss and the distillation loss. The distillation loss captures how closely the student network mimics the teacher network. And then gradient descent is applied to the student network to jointly minimize both losses. So during distillation, we're interested in minimizing the loss on the training data set, but also making sure that while doing this, the network mimics the teacher network. Shared training is another way to trade off accuracy for some improvement in training time and memory usage. This is applied in the context of neural network ensembles when we are training a bunch of different models to perform the same task. The high-level idea is to train multiple networks in a shared manner. One approach to achieve shared training is tree nets. Given an ensemble of deep neural networks, tree nets combines the initial layers together to form a monolithic network with various branches. This monolithic network, which is called the tree nets, is then trained in an end-to-end fashion using gradient descent until it converges. Within the shared training approach, another technique is snapshot, which trains a single neural network architecture and forces it to visit different local minima. At every local minima that the network visits, snapshot maintains a copy or a snapshot of the network parameters at that minima, And these different copies are then used together in an ensemble. Recently, we proposed MotherNets, which is another technique to achieve shared training of ensembles of neural networks. And the idea here is, given a target set of networks that you want to train, first capture the structural similarity that exists between different members of this target ensemble, constructing the MotherNets in this particular way. This MotherNets is then trained using the dataset to completion. Once this network has been fully trained, it is used as a way to initialize each of the ensemble networks. In a way, we can think of it as providing a warm start to the ensemble networks, which are then further trained until they converge. And again, this process provides better training time and requires less memory overall, but comes at the cost of some loss in accuracy. So we've looked at how different approaches trade off accuracy to provide better training time and memory usage. Next, we're going to see how different approaches can trade off between the metrics of training time and memory usage. Recomputation is one way of achieving that. In this approach, the intermediate results produced during the forward pass are not stored at all, which means that the intermediate results do not have any footprint in terms of their GPU memory. During the backward pass, when these intermediate results are required, we perform mini forward passes, recompute the intermediate results, and then use them in the backward pass as needed. And this process continues for every layer in the network. Again, trade-offing some computation so that we don't have to store any of these intermediate results. Existing research within the recomputation space is centered on figuring out which of the intermediate results to store given a certain memory budget. The stored intermediate results can then function as checkpoints, and this recomputation or these mini forward passes only need to happen from these checkpoints instead of redoing everything from the very first layer. The first technique that was introduced in this space allocates these checkpoints in a greedy fashion. So picking those layers that have the highest computation requirement and just storing them. Recently, there has been work from the machine learning and systems community that is called checkmate. And the idea behind that is to formulate the allocation of checkpoints as an optimization problem, and then solve this optimization problem as close as possible to an optimal solution using an integer solver. Finally, the approach we're going to discuss that trade-offs training time for memory usage is that of offloading the results. The idea here is that during the forward pass, the intermediate results that are produced are stored in the CPU memory instead of being stored in the GPU memory. What this means is that the expensive GPU memory, which is more of a limited resource, is free and is free to be utilized for other purposes. Then during the backward pass, this intermediate results, when they're needed, are brought back into the GPU memory and then used as they're required. In summary, in this part of the tutorial, we looked at research to improve deep learning pipelines. Specifically, we organized this research in terms of how it trade-offs between various metrics of interest, including accuracy, training time, as well as memory usage.